Hey guys, let's quickly talk about pods, and basically we would be dealing on how to work with pods. So let's first talk about the theoretical portion of pod. So in the VMware and Hyper-V world, the atomic unit of scheduling is the virtual machine. So deploying workloads in these environments means stamping them out in VM. So in the Docker world, the atomic unit is the container. Even though Docker now supports services and stacks, the smallest and most atomic unit of scheduling is still the container. In the Kubernetes world, the atomic unit is the pod. So be sure to take this and tag it to your brain as important. Virtualization does VMs, Docker does container, and Kubernetes does pods. So these are very three important comparisons which you would be using as you go forward. So pods versus containers. At a high level, pods sit somewhere in between a container and a VM. They are bigger and arguably more high level than a container, but they are a lot smaller than virtual machines. Digging a bit deeper, a pod is just shared execution environment for one or more containers. More often than not, a pod only has one container, but multi-container pods are definitely a thing. For example, multi-container pods are excellent for co-scheduling tightly coupled containers, containers that share resources and wouldn't work well if they were scheduled on different nodes in the cluster. An increasingly common example is logging and services meshes. Now, let's talk more about pods, the canonical example. The example we all use when describing the advantage of multi-container pod is a web server that has a file synchronizer. In this example, we have two clear concerns: serving the web page, making sure the content is up to date. Now, microservices design pattern dictate that we should keep these concerns separate. One way to do that is deploy them in a separate container, one container for web service, another container for file sync services. This approach has a lot of advantages. Instead of building a mini monolith where a single container runs the web services and file sync services, we are building two microservices, each with its own separate concern. This means that we have different teams responsible for each of the two services. We can scale each services independently. We can also update them independently. And if the container running the file sync services fails, the web services can stay up, though it may end up serving stale content. However, despite designing them as separate autonomous services, it makes sense to run them side by side on the same node. Now, the simplest way to implement the shared volume is to schedule the two containers on the same node. By running the web services container and the file sync container in the same pod, we ensure they are deployed on the same node. We also give them a shared operating environment where both containers can access the same shared memory and shared volumes, etc. Okay, so let's talk. How do we deploy pods? Now, to deploy pod to a Kubernetes cluster, we define it as a manifest file and then post that manifest file to the Kubernetes API server. The master examines it, records it to the cluster store, and the scheduler deploys the pod to a healthy node with enough available resources. Whether or not the pod has one or more container is defined in the manifest file. Now let's go a bit more deep. The anatomy of a pod. At a highest level, a pod is a shared execution environment for one or more containers. Shared execution environment means that all containers in pod share the IP address, host name, sockets, memory, volumes, and more of the pod that they run inside of. Under the hood, a pod is something called a POS container. That's right, a pod just has a fancy name for a special container. This means the container that run inside of pods are really containers running inside of containers. For, you know, we can go more and if we see the movie Inception by Christopher Nolan starring Leonardo DiCaprio, we have more details. Yeah. So on a serious note, the pause container is used to create a common set of namespaces that all other containers in the pod will inherit and share. This includes networks, UTS, and IPC. In network, it is IP address, port range, routing table. In UTS, it is host name. And in IPC, we have Unix domain sockets. As we just mentioned, this means that all containers in a pod share a hostname, IP address, memory address, space, and volumes. Let's move a bit closer. Each pod creates its own network namespace, a single IP address, a single range of ports, and a single routing table. This is true even if the pod is a multi-container pod. Each container in a pod shares the pod IP, range of ports, and routing table. Each container in pod shares the pod entire network namespace. This includes local host adapter, port, range, routing table, and more. But as we already discussed, it's more than just networking. All containers in pod have access to the same volume, the same memory, the same IPC sockets, and more. So technically speaking, the pause container or the pod holds all the namespaces any container in the pod inherit and share these pod namespaces. This pod networking model makes inter-pod communication really simple. Every pod in the cluster has its own IP addresses that's fully routable on the pod overlay network. If you read more on installing Kubernetes, you have seen what we have done in the past. We have created a pod network at the end of the play with Kubernetes and manual install section because every pod gets its own routable IP. Every pod can talk directly to every other pod. No need to mess around with things like, some port mappings or something. Now, intra-pod communication, where two containers in the same pod need to communicate, can happen via the pod localhost interface. If you need to make multiple containers in the same pod available to the outside world, you do this by exposing them to individual ports. Each container needs its own port and two containers in the same port cannot use the same port. In summary, it is about the pod. The pod gets deployed, the pod gets the IP, the pod owns all of the namespaces, the pod is at the center of Kuberverse. Now let's talk about pods and C groups. At a high level, control groups or C groups are what stop individual container from consuming all of the available CPU, RAM, and IOPS on a node. We could say that they are police resource usage. Individual containers have their own C group limits. This means it is possible for two containers in a single pod to have their own set of C group limits. This is powerful and flexible model. If we assume the canonical multi-container pod example from earlier in the chapter, we could set a C group limit on the file sync container so that it had access to less resources than the web service container and was unable to starve the web services container of CPU and memory. Now let's talk about atomic deployment of pods. Now, deploying a pod in an all or nothing operation, there is no such thing as partially deployed pod. For example, either everything inside of a pod comes up and the pod becomes available, or everything doesn't come up and the pod fails. For example, you can never have a situation where you have a multi-container pod with one of its container up and accessible but the other container in a failed state. That's not how it works. Nothing in the pod is made available until the entire pod is up. Then once all pod resources are ready, the pod is made available. It also important to know that any given pod can only be running on a single node. This is same as container or VMs. You can't have part of the pod on one node and another part of it another node. One pod gets scheduled to one node. This principle is at the heart of the pod's co-scheduling ability. If you need two container services to run on the same node, deploy them on the same pod. Okay, so I think we pretty covered a lot of theory, and I'm taking a pause here. In the next lecture, again, we would be talking a few more interesting stuff, and then we'll go ahead with that. Thank you.